Welcome to this video where today we are going to explain about simulation of permutation test. Permutation tests are powerful statistical tools used to determine the significance of experimental results. This presentation explores the simulation process, application and interpretation of permutation test in data analysis. First, what exactly is a permutation test? It's a non-parametric method, meaning it doesn't assume a specific distribution for your data. Instead, it relies on randomly shuffling the data to test the likelihood of your observed results. This is key in hypothesis testing, where we compare observed statistics to those generated by randomly permuted datasets. Before running a permutation test, there are some important prerequisites. First, the data must be exchangeable under the null hypothesis, meaning we can freely shuffle data points without changing the nature of the test. Next, independence between observations is critical to ensure accurate results. Finally, large sample size improves the test's power. Now, what are the procedures to do a permutation test? First of all, start by calculating your test statistic using the original data. Then generates thousands of permutations by randomly shuffling the data levels. After that, recalculate the statistics for each shuffled data. And at last, you compare your original statistic to this new distribution of permuted statistics. The goal of permutation testing is to build an empirical distribution. This involves generating thousands of random data rearrangements through simulations, computing the test statistic for each rearrangement, and compiling these to form a distribution. From here, we can easily assess how extreme our original statistic is. Once we have built the permutation distribution, determining the p-value is very simple. We count how many permuted statistics are more extreme than our observed statistic. Then we divide this count by the total number of permutation, giving us the p-value. If it's less than 0.05, we reject the null hypothesis. Otherwise, we fail to reject it. Here I have the example of a permutation test that I have done in my copy. Suppose you have two groups A and B, where at first I found the original test statistics of these two groups. After that, I combined the group and I found the permutations of randomly shuffled levels. Now we should repeat this step many times, and to calculate the p-value we have to count how many times the permuted test statistic is extreme or more than the observed value, that is minus 3.66 in this case. If 40 out of 1000 statistic is greater or equal to minus 3.66, then the p-value is 0.04. Since 0.04 is less than 0.05, you reject the null hypothesis.
Permutation tests offer several advantages. They are flexible, accurate, robust, and easy to explain. Even with small samples, they provide exact p-values and they are less affected by outliers compared to parametric tests. While permutation tests are powerful, they do come with limitations. First, computational intensity can be a concern. Large dataset requires significant processing power to generate all those permutations, which can be time-consuming. Permutation tests are widely used in fields like neuroscience, genetics, and ecology. From analyzing brain activity pattern in fMRI studies to identifying genetic variation in population and accessing environmental changes, the applications are endless.
And that's the beauty of permutation tests. Thank you for watching this video. I am Prashanta Acharya alongside with my teammate Srujan Subedi, and we hope you found this exploration of permutation tests insightful. Thank you.